Hi everyone. For years, scientists were divided were cathode rays waves or were cathode rays particles. Today we will see how J.J. Thomson settled this debate once and for all. Crookes provided that cathode rays exist and showed several properties. But he could not answer three important questions. What is the charge of this particle? What is their mass? Are they same in every gas? Different for the different gases. So J.J. Thomson realized that this debate would only be settled through the quantitative measurement. To identify a particle, scientists normally measures charge and mass separately. But this was impossible because electron could not be isolated individually and their mass was extremely small. Even atomic masses were not even accurately at that time not determined. So compared to atomic mass, electron mass 2000 times less than the atom mass. So Thomson realized that instead of measuring charge and mass separately, why not measure their ratio? E by m. This called charge to mass ratio. So to determine it, Thomson needed to know how cathodes respond to the forces or like electric and magnetic forces. So before we go into the details of the J.J. Thomson experiment, let's first look at what scientists already knew at that time about the electric charges, electric field and magnetic field. This helps us understand how J.J. Thomson used these ideas to uncover the true nature of cathode rays. So, what they know about the electric charges? Scientists knew that there are two types of electrical charges. What are they? Positive charge and negative charge. They know it. And positive charges attract each other. Opposite charges attracts each other, plus attracts minus. Like charges repulse each other. Means minus repulse minus, plus repulse plus. Then what about electric field? How electric field can be generated? A charged object creates an electric field around it. Okay, so then how this field can affect others? Any charged particles entering this field experience a force and may change its path. So this field can affect any other moving charged particles. How? They may attract it or they may repulse it based on their charges. So whenever any charged species enter into the field, so once the electric force gonna act on the charged particles. Next, what they know about magnetic field? Scientists found that moving charges are associated with magnetic field and external magnetic field exerts a force on the moving charged particles. So as a result, see, now we can see here the diagram, positive charge particles moving this direction. But since it is once it is after entering into the magnetic field, So magnetic field force acts on these particles and it is changing its path. Before the field it is in a straight line, right? But after the field, because of the field, it is changed this straight to curved path. So the magnetic force changes the direction of motion and can bend the path into the curve. Here the path is curved, but in the case of electric field is either pulls or pushes the electron based on their charges. But magnetic field direction, it is acting on direction. So it changes direction path into curve path. This is something very important. Okay, these are the information they already know at the 18th century. Now come back. So nature, now we know that the scientific world is divided into two groups. One group is believing that waves, another group is believing that they are particles. Okay, if they are the waves, okay, so how they will react with the fields? Okay, so according to existing knowledge at that time, okay, so now let's talk about the wave nature. Many scientists believe that cathode rays might be a type of wave similar to light. If that is the case, what are the properties they has to have? They supposed to possess. The waves should travel in waves travels in a straight lines, and wave can produce shadows. Waves are not attracted towards positive or negative charges. Since already these two properties cathode rays are showing, cathode rays are traveling in a straight line, and so waves and also they cause shadows. These are already there. Now only thing we have to check whether now the cathode rays are attracted towards the positive and negative charge or not. This is we have to verify. If they are wave, they should not attracted towards positive or negative charges. Okay, what if now if the cathode rays are really charged particles, not waves, if they are particles, then they should respond to the electric and magnetic field. If they are waves, they should not be attracted towards the positive or negative plates. Now, are cathode rays waves or particles? That's why J.J. Thomson entered into the now he wanted to settle the war or the conflict, right? So J.J. Thomson used this knowledge, this information. J.J. Thomson used this electric and magnetic fields as a powerful tool to reset how cathodes behaves and to answer this fundamental question. To prove whether they are particles or they are waves, what he has to simply have to test with their response towards the electric and magnetic field. So by using this knowledge of electric and magnetic forces, Thomson designed simple, brilliant experiment that changed our understanding of matter forever. Let's see how he proceeded. So something you have to remember, this is very important note to remember. Remember, electric fields pulls or pushes the charges, pushes the particles based on their charge. But magnetic field, they bends or they curves their path. So J.J. Thomson designed a series of experiments using electric and magnetic field. So why? To find out the nature of cathode rays, and the main goal is to measure the charge to mass ratio. To find out the charge to mass ratio, first he wants to know whether they respond to the magnetic and electric field. So, electric field experiment. So, in this experiment, so what he did? So, two parallel metal plates placed either side of the discharge tube. This is extra included to the discharge tube. So, without electric field, as we can see here, so cathode is traveling in a straight line and hitting and forming a spot of bright light on the zinc sulfide coating here. So they are supposed to form here, the spot should be here because they travels in a straight line. But after inserting electric field to it, so what happens? According to existing knowledge, the charged particles experience a force in electric field, but waves are not attracted towards positive or negative plates. So these are the, if the cathode rays are waves, they should not be attracted to either positive plates or negative plates. If the cathode rays are, if the cathode is a charged particle, then they will experience the field, they will move any either side of the plates, right? So if the cathode is a charged particle, the beam will bend towards the positive plates. If they are waves, the beam will not bend. But what is we observed here? What is observed? So the beam deflected towards the positive plates, as we can clearly see here, is moving this charge. As we know from the basic knowledge, who attracts each other? Likes or opposite? Opposite charges attracts each other. Since this is our positive plates, so it is going towards the positive, so that would be what? Minus. So this observation concludes. What is concluding? The cathode rays carry negative charge. This result rules out the wave theory. Why? So we know already that waves should not attracted either side of the plates. If it is attracted, then it's not a wave. So the cathode rays carries negative charge. They are not a abstract things, they are particles because they having negative charge. Yes, let's move to the experiment 2. So magnetic field experiment. Now here we applied magnetic field perpendicular to the direction of cathode rays. So according to existing knowledge, magnetic field exerts a force on the moving charged particles, and the force is perpendicular to the direction of the motion. So expected beam will be deflected and may follow a curved or circular path if it is charged. If it is a wave, no deflection if there is no magnetic field. Okay, so if it is a charged particle, it will deflected if the magnetic field is there. If no magnetic field, no deflection. Okay, so if there is no magnetic field, our particles traverse in a straight line and forms a bright spot over here. But what we observe here, what we are observing here, see the path changed, curved here. The path is curved and changing their direction. What is the observation? The beam is deflected and describes a circular path. The magnetic force provides the centripetal force. What is this? Let's come over here. Yeah, we can see here. So the magnetic field bends the cathode rays into curved path. Yeah. So the force required to keep any object moving in a circular path is called centripetal force. It works towards the center of the nucleus, inverse, right? And so this in physics we will call as the force is required to keep any object in a circular path is called as, in the physics, the force we will call them as a centripetal force. So look at in our case also it is curved here. Why it is curved? So before the field, so the path is not changed, they are traveling a straight line, but when the magnetic field is applied, that is curved. So means because of the magnetic force it is curved. As we know from the basic physics, the force which is used or required to keep any object moving in a circular path is called as centripetal force. Since in the magnetic field, the magnetic force is responsible. This is changing the path. This is changing in the curve. So that's why here, so the centripetal force on the cathode, so the magnetic field is considered as a centripetal force. Sorry. So therefore, Thomson equated magnetic force equal to centripetal force. This is very important. And use this relation. So what is a magnetic field force? Magnetic field force is equal to the charge of the particle, velocity of the particles, and applied magnetic field strength. Okay, so this is equal to the centripetal force. Centripetal force equal to what? mv square by r, mass of the particle, velocity, r is the radius, right? Yeah. So now this relation, so J.J. Thomson used this relationship in mathematical calculation. So don't worry, like if the centripetal force is new to you, you will study in detail in your physics under the circular motion. Okay, so yeah, this information is enough for us. Okay, here let's continue our discussion. So what we observe now, so in the both electric field experiment and magnetic field experiment, Thomson observed that the cathode rays beam deflated. So this means that both electric field force and magnetic field force were acting on the cathode rays. So now Thomson had a interesting idea. What is that? So what if the electric force and magnetic force were applied in opposite direction? So since, okay, let me draw here, it's not there in the diagram. One second. Okay, so here this is our cathode. One second. Yeah, so now, so this is under the electric field, plus and minus, this is under magnetic field. So applying on electric field, it is moving upward. Okay, so now arranging magnetic field, so perpendicular to the path of the rays, now it is depicted downwards. What if we apply both fields at a time simultaneously. Electric force and magnetic force were applied in opposite direction. So that is what is idea. Since both forces are deflecting, if we apply both forces in opposite direction, what they do, the both forces exactly if the same magnitude if we apply, they would cancel each other. So if it is depleting upwards, let me take a scale like roughly 1 centimeter is giving like up is giving minus 1 centimeter. If both are applying together, so then both will get cancelled, and then we will see our bright spot in the middle without depletion. As a result, the net force, if we apply both forces opposite direction with same magnitude, so they cancel each other. As a result, the net charge on the cathode rays would become 0, right? So, and if no net force is acting on the particles, so then the beam would no longer bend. So they travels in a straight line with any deflection, isn't it? So Thomson carefully adjusted the strength of the electric field. So first he applied the magnetic field. So now as a result what happens, this is bended downward. Then slowly he applied electric field and he adjusts the field strength until to reach the deflected point at over here. Slowly he adjusts the magnetic field. By increasing the magnetic field strength, it is slowly moving the spot upward until reaching the same point. So he adjusts the field strength. So at this spot, so the both field strength is cancelling each other. That's why no deflection is observing here. Okay, so until the bright spot on the screen return to its original. Original means without any electric field and magnetic field. Where it is positioned? It is here, right? So he adjusts the field strength to reach its original, return to its original position. At that point, so here it is bended because Fe. What is Fe? Electric field force is working on the cathode. That's why it is bended. Here, why it is curved here? Because here Fb is acting on the particles. What is Fb? It is the force of magnetic field. So now, if both fields are applied, so if their magnitudes are equal, so then we observe the particle is returned to their original spot. So in this point, in this moment, so why there is no deflection means both magnitude of the forces are equal. Fe equal to Fb. What is Fe? Fe is a force of electric field. And Fe equal to what? Small e into capital E. What is small e? Small e is equal to charge of the particles. And capital E, field strength. And Fb equal to what? This force of the magnetic field. Magnetic field. So Fb equal to formula EV capital E. Capital B. What is E? Charge of the particle, velocity of the particle, and magnetic field strength. Since Fe is equal to Fb, can we write like this? Small E into capital E equal to small e into V into B, and these two get cancelled. Now, so from this can we write velocity? We can determine the velocity, right? We know the applied electric field strength, and also we know the applied magnetic field strength. From this we can calculate velocity. So what is our aim? Why we started this experiment? We want to calculate E by M ratio. So as I told you, since the path is curved, so here magnetic field force is acting as a centripetal force. So can we write Fe, electric force, that is nothing but E, sorry, one second. Let's give this numbering. This is equation 1. Now here, since it's curved, so now force of magnetic field E V B equal to M V square by R. This is centripetal force. Both are equal. So here FB is acting as a centripetal force. That's why we can write like this, right? So now let's simplify it. So here we having V square, V get cancelled. Now E B equal to what we got here, M V by R. Yeah, MVR by R. So let's substitute V value in this equation. This is equation 2. When we substitute that, E B equal to M R, what is V? Capital E by V. Okay, so E B equal to, can we write M E by B R. So what we want? We want E by M. Let's take M this side, B this side. So E by M equal to what we got here, E by B square, sorry, one second, B square R. So this equation J. Thomson used to determine E by M ratio. And so the calculate by using this method, so Thomson found E by M ratio 1.7, approximately, not exactly, approximately is equal to 1.76 into 10 to the power of 8 coulombs per grams. So if we convert into kilograms, then add 10 power 3 to it, 8 plus 3, 11. 1.76 into 10 to the power of 11 coulombs per kilograms. So this was an incredible achievement for the year 1897. Why? So see, at that time measuring the mass of the atom itself very difficult, but here the particle is smaller than the atom. How much? Nearly 200 times smaller than the atom. And how he calculated E by M ratio? Without any expensive instrument, any nothing, just simple, by using simple electric field and magnetic field. So this is something amazing thing. So he was measured the particle much smaller than any known atom. How? Just by using simple electric and magnetic field. So due to limitations in instruments of at that time, there were small experimental errors. So later scientists repeated this experiment with more advanced equipment and obtained the more precise value. So but even though the value of the whatever he calculated, that is very close. This is 1.76, this is 1.7588. Okay, so but this is more accurate modern value. This you have to remember for the exams. Okay, yeah, either maybe board exam or competitive exam. Better remember the modern value. What is that? How much? 1.758820 into 10 to the power of 11 coulombs per kg. This is the accepted value. The small difference for the Thomson value is due to the limitations of the early technology, but this result was remarkable and close to the modern value. So the accurate, yeah, so that's it. Just remember the modern value. Nothing to discuss more on that, but something you have to remember here, more important things. So electric force. So electric force pulls and pushes the charges, depends on their charge. Okay, but magnetic field bends the path of the moving charge particles. Why it is called as a centripetal force? So the magnetic force acts towards the center of the circular path and providing the required force to keep the particles moving in a circular path. It just acting as a centrifugal force. That's why here in the calculation we use the magnetic force is equal to centrifugal force. This is why both formulas are used in the calculation of E by M ratio. So Thomson experiment provides that cathode rays are streams of negatively charged particles, electrons. So by doing this, by calculating E by M, so he proved that this by is quantitative measurement, he forced the scientific world to accept that Dalton's indivisible atom was officially broken. So he proposed that the cathode rays which are generated in the tube are particles, and he named them as electrons. But the story is not ended yet. Still he wanted to prove something. What is that? Whether the behavior or nature is a property of particular gas or it is independent of the other different gases. Yeah. So because if it is a universal property, so then he has to prove that, right? So now, so Thomson experiment with different gases. So Thomson want to prove that whether the nature of the cathode rays are they same in every gas or different for the different gases. So to confirm that, he repeated same experiment. He repeated his E by M experiment by using different gases in discharge tube. So what are the different gases? Hydrogen gas, helium gas, neon, argon, etc. And he calculated E by M ratio. So irrespective of gases, but what is the calculated value is constant. Is dependent or independent? Is independent. Whatever gases you will take, they are giving same E by M ratio. Why? Now we know, every atom contains subatomic particles same. They are made up of same fundamental particles, electrons, protons, neutrons. When you ionize it, they releases electrons. So electrons, it is independent. It is not. It is a independent nature of the atom. Whatever atom you will take, right? Even like a simple analogy, Indian. If you got any person, the Indian or African, whatever, or American, so we will see the color of the blood is what? Red. That is not depends on the person, isn't it? Like that. So subatomic particle is a universal particle. So the cathode negatively charged particles are electrons. If you take hydrogen, only the thing what will changes. So since different atoms is having different valence electrons, so number of electrons may be different, but their nature, their charge is same, right? So that's why this experiment proved that E by M ratio remains same for all the gases. Therefore, E by m is independent of the nature of the gas. This is something very important because later we will compare E by m ratio of the protons and electrons, right? So, for the electrons, electron charge, so electron is a fundamental particle. It is common in all the atoms of the gases. That's why if you whatever gas is ionizing in the discharge tube, they releases same electrons. Since they all are electrons, their behavior in the discharge tube is same. Their charges also same. Okay, that is the conclusion. So no matter which gas you use, the value of E by m is same. This means the cathode rays are made up of same negatively charged particles in every case. Different gases only change the number of the particles produced because their valence electrons are different. Number of electrons coming from the atoms may be different, but they all are negatively charged particles. Yes, so that's what here, all the gases producing same negatively charged. So therefore, cathode rays are not a property of any gas. They are the stream of negatively charged particles common to all the gases and all the matters. So final conclusion, hence the cathode rays are the stream of universal subatomic particles present in all the matters. So matter is made up of atoms, atoms is made up of subatomic particles, all atoms contains what? Electrons. So Thomson experiment proved that cathode rays are independent of their nature of the gases. So these are universal subatomic particles of electrons. So why you want to conduct this experiment, whether these electrons is common, they are the fundamental particles of the atom, to prove that. So he conducted with different gases and concluded that these are the universal subatomic particles, and he named them as electrons. Yeah, so in our next video we will discuss Millikan's oil drop experiment and see how Millikan determines the charge of the electrons. Thank you.